Welcome back to Math 168. I'm Professor Robert Needing. We're covering section P1, Probability Rules. In addition to having the Probability P1 section handout from your PPTX, from your file, you're also going to want to have the addendum question 22 P1. And you can find that directly in your course underneath of your in-class lecture notes. And if you scroll down and you find P1 PPTX, you'll also find question 2 sitting right next to it. Have both of those available. This is an expanded version that goes into here. So when we talk about probability rules, what we're really talking about are three basic things. We're talking about an experiment which is performed, and it's a process by which an observation is made. We flip a coin, we draw a card, we make some kind of observation based on data that we are collecting. There's an outcome. An outcome of an experiment is a result that is obtained when performing the experiment. So we do the experiment, and the experiment can be repeated over and over and over and over and over again. And as we get those values, what we see is we see an outcome. So an outcome may be pulling a jack of hearts. An outcome may be pulling a green marble. An outcome may be how many times something happened out of something else, depending upon the experiment. The collection of all these outcomes is a sample space. So we perform an experiment, we get an outcome, and we get another outcome, and we get another outcome, and we get another outcome, and we put them all together. It's referred to as a sample space. Example, rolling a die is an experiment, and you will get, and something will happen when you roll a die. You get a 1, 2, 3, 4, 5, or 6. That's your sample space. What is the outcome of getting a 1? The outcome is 1 out of 6. Why? Because there's only one number 1, but there are 6 different numbers that can take place. So the outcome is actually something taking place or something happening. When we're talking about an event and a probability, it says when performing an experiment, we're interested in a particular collection of outcomes. In other words, a subset of which is of this event. When we speak of it, we speak about the probability of event A. We write it P parenthesis A, which is read P's probability, or the probability of A. It's the measurement of the likelihood that this event takes place. And it always isn't an A. It can be the probability of rain, the probability of a girl, the probability of a second marriage, the probability of a 90% or better. It can be the probability of anything we measure, and it can be a probability which can be fairly complex. Some examples are the probability is, or some examples, some facts are that the probability is always between 0 and 1 instead of percentages. We don't use 50%, we use 0.5. We don't use 75%, we use 0.75. Probability is always referred to as an event. The probability of A equal 1 means that it will definitely happen. The word definitely is associated with a 1 because it has 100%, 1.0. It definitely has to happen since the scale only goes from 0 to 1. Likewise, on a probability of 0, it means it's definitely not going to happen. So really what we do is we create a sample space, and a sample space of outcomes, if you will. And the sample space of outcomes, excuse me while I'm adjusting just a little bit here. There we go. The sample space of outcomes is somewhere between 0 and 1. And it's inclusive in between those numbers, so 0 to 1. So again, the closer we get to the center, the more even the distribution of the probability, and the further we get to one side, the more likely that it is, and I'll blow this up for 1 second, the more likely it is to happen for certain, or the more likely it is not to happen at all. And anywhere in between is a combination of those. Example, the probability it rains today equals 0.3, so we have less than a 0.5% chance. The probability of getting head when you toss a coin, exactly 1/2, because a fair coin has a head and a tail. Equally likely outcomes. If all possible outcomes are equally likely, the probability of an event is the number of ways A can actually happen divided by the total number of ways. And by that we mean if we have 52 cards in a deck, and we want the probability of pulling a jack. And again, that's the event. What is the probability that this event will take place? There are 4 jacks in a deck. There are 52 cards, and therefore there are 1 out of 13 in a reduced format. Now, when we talk about combining an event, so in the picture, it shows that we have event A and we have event B. If we're speaking of event A and B, and I'll highlight that designation, key terminology here, and, what we're looking for is the probability that both event A and B will happen, only the dark shaded area that you see on basically the overlap. And really that's what you want to think about when you think about and. You want to think about the overlap area. It has to happen here and it has to happen here. It has to be true in both, because this horizontal band or this horizontal row here, this is all event A. Things can happen here and are still part of event A. Things can happen here and still are a part of event B. But it takes things here and here to happen to be in A and B. I want to show you that a little bit differently I want to make a thing that we can refer to here. So let's say that we have event A, and let's say we have event B. Well, there's other things going on also. Maybe there's event X and there's event Y. So when we talk about A, there are things that happen in A. 7 things happened in A and 3 things happened here. So in event A and event B, 7 things happened. In event A and event Y, 3 things happened. But in total, 10 things happened in event A. So it's not the entire event, it's a intersection of the event. If we look at event B could have 7 things, maybe 1 thing here, so a total of 8. And event Y could have 3 things here, and let's put 5 here for 8. Well, we can see that the total here is 16, no matter how we look at it. The total sample space is 16. And if we look at something and something else, so if we look at X and Y, then X and Y are 5. X and B are 1. A and 7, or A and B are 7. A and Y are 3. The and notation indicates the intersection. Now, when we talk about or is completely different than and. Or doesn't matter if it's in A or it's in B, or if it's in both at the same time. So if we look back at the chart I created, if I'm looking at A or B, it could be any of this here. It could be this one, or it could be this one. If I look at B, it could be this one, or it could be this one. Now, think about how we're going to do that, though. Now, if we're going to look at event A, we're going to take everything in this row here. 7, I'm going to list them. So we're going to take the 7, and we're going to take the 3. We're going to take both of those things. And we don't calculate it actually this way. I'm just trying to prove a point here and show you what's going to happen. So event A, I want this thing, and I want this thing. Well, if I'm doing or B, I want this thing, and I want this thing. But let's notice that I have double counted 7. I counted it once here, and I counted it again here. This value got counted twice. So when we're doing an or calculation, when you see me subtracting something shortly, you'll understand hopefully why I'm subtracting something, because we double counted that value. However, though, for you right now, the picture grand scheme is only the dark for and anything blue for or. The conditional probability. Conditional probability says the probability of A if. So the notation here is if. Probability of A if B is the probability of A. So I want the probability of the first piece, the A part, given or if I know that B actually takes place. So I have to be guaranteed, first of all, that the if part has taken place or happens. And from there, I'll calculate what does it take for me to get the actual probability of A happening. So for instance, if I went back to my piece here, what's the probability of event A happening if I know event Y happened? Because event A has this and this probability of happening. But event A only has a probability or has a modified probability if I'm guaranteed I'm only looking in event Y. So if guaranteed this took place, then this has nothing to do with it. An if statement locks itself into a row or a column before it goes to look at the probability of that event. And you'll note it by the if value right here. You'll want to definitely pay attention if it says if. And this will be our formula for if. Now, another good notation to make at this point in time right now is that back in your modules and your area of Hangout, I will post for you a student resource, and that student resource will be in here. It will actually be a set of values for you to print and keep. And I'll show you mine. I have it posted into a different class of mine right now, similar to yours. And go to modules. It'll almost be identical to your class, but it's a different class right now. And if you notice right here, it's called Formula Sheet SP19. I'll be posting yours soon. And Formula Sheet SP19, you'll notice, is a formula sheet that you can use on all examinations, all quizzes, things like that. It's got a lot of formulas we haven't covered. However, though, look at the very top, and it's got all of the probability that we're doing tonight. So you'll know how to do this entire top by the time we're done with this particular lecture. So the conditional probability. The probability of F if R is not the same as the probability of R if F. You can't turn these things around. The complement rule is something we'll use continuously. The probability rule says the probability of not being A is equal to 1 minus the probability of actually being A. How can we use that? Well, let's say that in this problem up here, what's the probability of A and B happening? Well, the probability of A and B happening, there are 7 A and B's out of 16 things. So I have a probability of my A and B, which equals 7 out of 16. So let's say that without going up here, and let's say that I want the probability of not A and B. Well, I'd have to go in and get each one of these other things that aren't A and B, which is this one, this one, this one, those kinds of things. And I'd have to combine all this together, and I'd have to do that. But the complement rule says that if you know this is A and B and you want not A and B, then you can take 1 minus 7/16. And you can simply do the math from there. Well, 16 minus 7/16 is going to be 9/16. And of course, I would divide these and get decimals. Okay. But I want you to notice, okay, so I said the answer is 9/16. This is the only thing that is A and B. 3 plus 1 is 4. 4 plus 5 is 9 out of 16. 9 out of 16. The complement rule does it very quickly and very nicely. And again, we would also turn these into decimals. We'll get to that in a second. Translating conditional probability from English to math. Okay. If you need to know when to put the conditional P or if it comes after if, because it can be tricky sometimes. So what we're identifying here are the values of what is the probability and what is the given condition. It says given probability of A if F, identify A. So with the first value, it's not going to actually be an A, it's going to be something. Identify A immediately after the word probability. Then identify B immediately after the word if. So the thing that comes first is the thing that you're looking for the probability of. The thing which comes second after the if value is the part that has to be true or has to take place or has to be known before you start. I like to think about it as B has to happen before I can get the probability of A. In this exercise, we're going to figure out which of these items are which. So first of all, and I've kind of underlined this, and I've done a little bit of notation on my piece of paper to make it easier, so I think I'm going to share that with you. So first of all, probability of being pregnant given that you are female. Okay, so we have to go into that problem. We got to think about, okay, what part of that problem has to happen first, and what part do I actually want the probability of? So I'm going to use blue, and we're going to find all the probability things first. So first of all, we want the probability of being pregnant. Okay, definitely. Then what has to take place? Given that you have to, first of all, be a female. So really, I'm going to back off a little bit on this one up here and say, well, you know what? It's not probability of all that stuff being pregnant. What I really want to have is just what's important. And the part's important is being pregnant. So I want the P of pregnant if female. Okay, well, what does that look like when we write that out? So if I want the probability of pregnant if I am female, I want P probability being pregnant if female. Now, another way we write that also, I want to make sure you understand, is the probability of pregnant, big slash line here, given female. Often you'll see me write it this way. This means the same thing. P if F. Second one. What's the probability of being female? So now as we change, I want the probability part for a female, and I want you to be pregnant first. Okay, well, probability female if pregnant first. What's the probability of getting a ticket? So probability comes right after it, getting ticket. Okay, so the ticket part is my first part. Given that, given, this has to happen. If this doesn't happen, I don't get the probability. I'm speeding. You know the bus drivers are on strike. It doesn't say anything about probability here. This is what is given. It just happens to be first in the sentence. You want to know the probability. There it is. So what are the odds of arriving late at work? Probability that I will be late if I know I was speeding. Or excuse me, the bus drivers are on strike. I was in the last one where I was speeding. If you play with fire, so this is the given condition. This happens first in the sentence. How likely is it that you will get burned? Okay, so the likely, probability, chances of, they all mean the same thing. Probability I will be burned if I decide to play with fire. Now this one is pretty wordy. We'll make sure we understand why this happens the way this happens. So what is the probability that a comedy has Warner Brothers in its producer? Okay, so first of all, what's the probability? And now it interjects this word, that a comedy. This is the if part. Probability that a comedy. So it's telling you you have to be a comedy in order for you to be Warner Brother as a producer. What is the probability of Warner Brothers if it's known to be a comedy? A little bit wordy, a little bit hard to understand, but I think you can get it out. The hard part for students on this one is probability, and the first thing you see is comedy. Then we'll put comedy first, but it's kind of like an introductory clause where this has been entered, and then it goes on to talk about the true piece that we're looking at. Let's keep going. So here's some probability rules, and these rules are the same rules that I just showed you a couple minutes ago in that formula sheet right up here at the top. Here's the formula sheet up here, and here's the very top ones, and it's the very same ones that we're talking about here. So the top one is the or. Remember a little bit ago, I just got done telling you, I said, you know what, when we come back, we're going to have a problem because we double counted. I'm going to want to subtract something. I'm going to have to get rid of one of these. I'm going to have to lose one of these. Okay. Well, why do I have to lose one of these? Because again, they were double counted. I counted them in the row and I counted them in the column, counted them too many times. This very first problem right here, you'll notice that one of the things it does is it subtracts the probability of A and B. Why does it subtract the probability of A and B? Because we double counted it. This is the OR situation. In the OR situation, we'll take the probability of A, we'll add it to the probability of B, and then we'll subtract away one of those double counts or one of those A and B's. In an AND situation, we'll take the probability of A and we'll couple it with the probability of B. We'll divide it by the value of A if B, and I'll show you that math and show you how that takes place. It kind of lays itself out nicely when you look at an AND situation. Okay, so here's your OR right here, and then here's your ifs right here. The probability of not A, that's the complement rule I just did for you a minute ago. Complement rule is 1 minus probability of A. The probability of A if B. Now, in A if B and B if A, they're backwards from each other. And here's what you'll notice, and here's what I try to tell students, is that the first one, remember, that's the one with the probability of. Okay, we were just talking about these. And this is the one I want the probability of. Okay, I want the probability of the thing which happens first. Notice the thing that has to happen is the thing I divide by. And the thing that has to happen is the thing that I divide by. Both of them utilize exactly the same numerator. They both take the calculation of A and B at the same time. So all we really have to nail down here is which one happens first in order and which one happens second in order, and we should be able to make the calculation for this. I think that maybe this would be a good place to go off and go do some of these. So why don't we jump to question number 22. So go get your hand out for question 22. Stall the video for yourself if you have to. Matter of fact, I'm going to stall it because I need to grab mine and I'll be back. You won't even know I'm really gone. Okay, see? You didn't even know I was gone, did you? So let's continue on and let's pull out that question and let's move forward with that question here. And mine is going to be worked on from here. Okay. So first of all, let's get a background for where we are here. So these are people who are inducted into the Rock and Roll Hall of Fame, and there are 303 total inductees in 2015. So of those 303 inductees, we have people who are performers, people who actually play musical notations, and then we have people who are not performers. We have people who are female, and we have people who are not female. Okay, they have no female members, so you're not a female if you're in here. We're going to do some calculation. Now, first of all, think about this event. This is the entire event. If I look at this entire event, all of these people were performers. All of these people were female. All of these people are in here. Let's start with letter A. It says, let F represent the event of having female members, and let MP represent the event of being a performer. They call it a music performer. So MP, music performer. So our first calculation is, what is the probability that an inductee chosen at random? So now when we choose at random, we're choosing out of all 303, is a performer. So that's it right there. So first of all, if I look at performers, there are 206 performers. So the probability of me having a performer or being a performer is 206 out of 303. Take your calculator, do the division, 0.680. Sorry, 0.680. This is my probability that I'm actually a performer. And it sounds proper that 68% of the people inducted were actually performers. There are a lot of people inducted in the Rock and Roll Hall of Fame who aren't performers. They run the behind the scenes kind of stuff. Or maybe mixers, I don't know all of them. But there's many more people than there are just performers. What is the probability that an inductee chosen at random does not have any female membership? So in other words, we want not female. Okay, well, let's do it this way. This is that not word. This is that complement. Let's actually go do the calculation for the people who are female. So if I look at female membership, it's 47 out of 303. So I'm going to do the complement, which is going to be 1 minus those who are female in the group. Because if I do this, I'll get not females. Okay, well, take your calculator, take 1 minus 47,303. You may have to change to a decimal when you do that. So a way you can do that You could, first of all, calculate 47 divided by 303, because you know you want a decimal, and there it is. You could take 1 minus, now you can go get that answer up top. So there's two ways to get it. You can go to second, and you can go to answer right there. Oops, I missed it. 1 minus second answer. See it? 1 minus second answer. And I'm going to get my 844 or 845. You also could have put it all in as one line if you wanted to. 0.845. However you do it, you got to get 0.845. What's the probability inductee chosen at random? So I'm back to the whole group again. Has members, if it's a performer. So now we got an if statement here. So the minute I see this, if it's a performer, I know that it's only in this column right here. Only in this column right here. Now, I'm going to do this a couple of ways. So the first thing I'm going to do is I'm going to look at the actual if formula. Okay, so I'm going to go back to my if formula. And right here's my if formula. Remember, my if formula is the and portion on the top divided by the if portion. And that's the way I think about it. And on top, if on bottom. Okay, so I'm going to go back here. The probability of this, so I need the and of F and MP. So I need the F and the MP. And I need to divide that by the if statement, and the if statement is MP. Okay, so what's the if and what's the MP? Okay, so first of all, F and P. So go over here, female and performer, 38 out of 303. I need 38 divided by 303. That's my numerator. I also need the MP, the music performer. These are the music performers. All of these people here are the music performer people. And the music performer people are 206 out of, again, 303. Let's turn our calculator on. Now, two ways. We went decimals for this, so I think that entering a fraction is kind of really not my deal here. So I think I'm going to take this, and I'm going to do 38 divided by 303. But be sure to put it in a parenthesis. Then I'm going to divide it by another parenthesis, which is 206 divided by 303. I'm going to close that parenthesis off. I'm going to hit the button, and I'm going to get 184. 0.184. Now, I like to use the formula because you're going to have to use the formula, so I like that. And yes, it's a little bit cumbersome, but once you get used to it, it's very, very good. Now, another thing I'm going to show you. So let's say that I have a table, and I'm lucky enough to have a table value, and I can do this. Okay, so it's the probability that this happens if this is taking place. Okay, let's go to if this is taking place. So MP, just in this row right here, right? Just in this row right here. Now, in that row right there, what am I looking for? I'm looking for female. Okay, I'm looking for female. And if I look at female, female is 38. Okay, and what happens in that row is the only thing that can take place is 206 different things here, and I'm locked into this row. So what happens if I take 38 and I divide it by 206? Well, if I take 38 and I divide it by 206, I get the same 184. How come? Because it's the same thing. It's the same thing if I can actually find the thing that I'm looking for out of the table and divide it by the place that I'm supposed to be. But what I find is most students fail. They go 38 divided by 303, and they don't get it correct. I'd learn to do it this way, but I'd learn to double check it that way. I'll do it again when we do the next one. Letter D. Letter D, right? A, B, C, D, D. So we are looking for, this one's a little more complicated in the words, but not in the math. We want the probability of not being a performer if, so here's another if not female. Okay, so first of all, we need the probability of not being a music performer. Well, if we look up here, we have the probability of actually a music performer. So we're going to use some complement stuff here, okay? Or maybe we'll go to not. I don't know. We'll see. All right, so let's lay this thing out. So we want the probability. Well, first of all, we want not MP, and remember we have to put the two of these together. Not MP and not female. We need that. And then we need also to divide that by the if statement, which is not female. Okay, well, let's go see if we can find this in the chart. Not MP, not female. Okay, go find up here, not a performer, not a female, and look for the intersection. The intersection is 88 out of 303. Okay, the intersection and is always this out of the whole value. So this top number is 88 divided by 303. There's my top. Not 88, 303. Now in the bottom, let's go find not female. Okay, well, don't we already know not female? 0.845. Once we start to get some of these questions answered, usually it falls together pretty nicely. And I'll encourage you to practice this because I can guarantee you it'll be on a test. Okay, so there's my first one right there. I did that one. I'm going to go ahead and get an answer. There's my numerator. I'm going to divide it by 0.845. And I'm going to get approximately 344. Boom, done. Now, notice the if is gone here. There's no if value over here. What is the probability that an inductee chosen at random is a performer with no females? I actually love that they write this sentence for you right now at the very beginning. Sooner or later, you'll have to write this, but it's a nice practice. The probability of music performer and not female. Okay, so we're looking for this and this to take place simultaneously. So let's go, first of all, let's go to the chart for this one. So first of all, I need music performer. Okay, all of these people here, right? I'm in this row of people right here, right? Not female. So I go here and I look for the not female position, 168. Okay, so I'm looking for, remember, I'm looking for this intersection here, and it's not an if statement. So since it's not an if statement, I'm going to go out of 303. 168 out of 303. The only time I'm going to divide by a row number or a column number is if it's an if statement, and this is not an if statement. This is a this and not this. 168 divided by 303 is 0.554. And the last one. What's the probability that an inductee chosen at random is either not a performer, or, here's an or, has a female? So this is the first time we've run into an or. So remember, this is the double count situation. So let's look at this first of all. I want the probability that I'm not a music performer. Okay, anybody in here counts. Anybody in, I'm going to circle it because I'm done with this question after this. Anybody in here counts. Okay. And then I want the or a female, right? I want or a female. Okay, well, everybody in here counts. But the 9 is getting double counted. The probability of 9 out of 303 is getting double counted. So how do we handle that? Okay, so we use the formula. Of course we use the formula. I mean, seriously. So when we talk about the formula, it's this one. We want the probability of A, the probability of B, minus the probability of A and B at the same time. Okay, so we want the probability of A, which is not a performer, plus we want the probability of F, female, minus we got to take away the probability of not a music performer and female. Remember, the double count. We got to get rid of one of those right there. Okay, not a music performer. I think we can get that from right here. Look at this. We know a music performer, right? I'm always looking for something that's already been done. I do not want to recalculate if I don't have to. Here's a music performer. We're going to do 1 minus 0.68. I got that one right there. That's the complement rule for that value. Female. Well, don't we know not female? Right here. We know not female right here. This is not female. So since we know not female, we actually know male, or we know female. So we're going to do 1 minus 845. And we're going to take away the intersection of these two things. Okay, well, remember what I said was being counted too many times, the 9. The 9 is our number that got double counted. 9 out of what? 9 out of 303. We didn't have that calculation anywhere, so we got to get that. Okay, all at one time into a calculator. Parenthesis 1 minus 0.68, parenthesis, plus, parenthesis 1 minus 0.845, parenthesis, minus the fraction 9 over 303. And when you enter all of that, you get 0. What did I get there? 445. Definitely a skill that you want to go over. If you need to go over this a couple times, go over this a couple times, re-listen to this particular piece. This is probably the most important thing that we're covering in P1, is being able to do this well. All right, back to where we were. If we talk about a disjoint event, so a disjoint event is an event that is mutually exclusive or disjointed. Two events have absolutely no ability to happen at the same time if they are mutually exclusive or disjoint. Flipping a coin and getting a head and a tail. It cannot happen in a event, because remember, an event is singular. I can't flip the coin and get both. I can't draw a card from a deck and get a heart and a black card at the same time. Okay? They can happen in two different events, but not a event. These things which we call impossible have a probability of 0. So if in a chart we were looking at a two-way table and we saw that the probability event was 0 for girl and some event A, then we would say that those two events are disjoint. Also, at the same time, it says the probability of OR equals P of A plus P of B. Well, just a minute ago, we did the probability of OR right here, and OR was A plus B minus A and B. Okay, so why is it saying it's the same as A or B? Okay, so if probability of A or B equals the probability of A, we just got done doing this, the probability of B, and remember, we got to take out the double count because it overlapped itself 2 times. It's A and B, but I just wrote A and because we know we took that out. It's saying in this question that, I lost it. Sorry. I lost my whole flyer. There it is. It's saying that this whole disjoint thing, that's saying A or B just equals A plus B. It's saying it just equals this. Well, that means this is gone. Why is this gone? Because there is no A and B. A and B is worth 0. And if you take away 0, you might as well have it be gone. I like to tell students, well, the A or B for this case of disjoint, this is only for disjoint. Don't confuse it with everything else we've already done. We're not changing the rules. It's equal to the probability of A plus the probability of B minus 0. So they know that they're really subtracting something that's a disjoint event. So it looks like this. So if we talk about a disjoint event, A and B have no overlap in them. In other cases, there's an A and B here. There's an overlap in the center. And this is the true OR right here. The true OR has a middle, which is an AND part, which overlaps itself, and it overlaps itself 2 times. So that's why we get rid of that double count feature there. Which of the following events are disjoint mutually exclusive? Well, when we talk about these two particular events right here, for example, tossing a coin. So when we toss a coin where A is an event that a head shows and B is the event that a tail shows. I already said that was a disjoint event. Drawing 10 Skittles, possible colors are yellow, green, red, purple, and orange. Let event A be that all 10 Skittles are red. Let event B be the event that at least one Skittle is orange. In A event, both things can't take place. A and B are disjoint. You can't have everything be red, but yet say at least one is orange. When we read from the table of the problems, as long as there's a value of 2 events is not 0, then the events are not disjoint. Okay, what does that mean right there? So if I create any chart, event X, event Y, event A, event B, if you see numbers in here, no matter what those numbers are, if it's an actual number, there's no disjoint at all here because these values have something going on at their intersections. However, if I change one of these, now I have a disjointness. I have disjointness between Y and A. Y and A are mutually exclusive because Y and A at their AND intersection have no value at all. This is how we would find disjoint from a table. It says independent events, A and B, are independent if 2 events have no effect upon each other. In other words, the probability of A and B is the same as the probability of A times the probability of B. And that's what that means in that second box. Tossing a coin and getting a head and then another head, they are independent of each other. If you flip a coin and you get a head, when you flip it again, the first event had no leadway or no influence upon the second event. The second event doesn't even know the first event happened. So the probability of A times the probability of A is 1/4 in this particular case. When aren't they independent? So let's say that I reach into a bag and I pull out a marble, and this marble is, who cares what color, I pull it out, but I don't put it back. I keep it. I have now modified the chances of reaching in, getting another marble, because I've lowered the amount of marbles inside of the bag. Same way for the lottery. When the lottery draws a number and they keep that ball, they have modified the events of all the balls that are remaining inside of there. So the chances have actually changed themselves of getting another value when that ball is gone. When you replace something, you don't modify the chances. When you don't replace something, now you've modified the chances of something taking place. Independent, you keep replacing. Dependent, you don't replace. Examples of independent events: probability of flipping a coin, landing heads up, and then a face card. The face card has nothing to do with the coin. One is not taken out of the other. They're independent events. Suppose we draw 2 cards with replacement. As soon as you see the replacement, that's all that matters. As long as it's being replaced, it's an independent event. Things which are deemed not independent: drawing a card and not replacing it. Drawing a ball from a box, not replacing it. Having a raffle drawing where first, second, and third prize are awarded in the same pool of participants. Because when you pull that first prize away, you've taken that away from anybody else being in the half of it. So you've changed the odds of winning the other events. This is a good question for us to end on in this particular section, and I'm going to give myself some space. Sorry if that was a little loud for you. So we are supposed to find some probability calculations here for A, not A, AB, and so on and so forth. So let's go do these. And I'm going to copy this particular thing down. So we have event B, and then we have not B. We have A, and we have not A. and we have 0.2. So the first thing I would have you notice is that there are values for everything. So therefore, there's no disjoint going on here. So if you're analyzing for disjoint, there isn't any because we have values for everything. And how about this? How about I'll keep this open so we can kind of see it. Let me shrink it back down. There we go. Perfect. And let me open up this at the same time, and let me go here. So give me a little second here give me a hot second to do a little modifying here. Boom, there we go. How's that? Okay. So let's go to our first calculation. Let's go to letter A. Letter A. Letter A says we should find the probability of A. Well, the probability of A is the sum of 0.2 and 0.1. 0.2 plus 0.1 makes a probability of 0.3. The probability of A is everything in A, and there's two probabilities, and we need them both. So the probability of A is equal to 0.3. We're going to do the same thing for not B. Letter B, we're going to do the probability of not B. Not B. By the way, the little tilde sign means not. That's why you see I have the tilde there. So we find not B. Not B is 0.1 and 0.3. Not B is 0.4. C. C wants us to find A and B. Okay, well, let's find A and B from the chart. So let's focus on the chart this time. I go to A. I go to B. This is A and B. A and B, these are relative frequencies in this chart. So A and B has already been calculated for me. You'll notice there's no total for me to divide by. I have to entrust the value that's sitting there. So 0.2 is my A and B. A and B. Nice when I already have, again, relative frequencies compared to counts. In the last box we did, we had to actually divide by the whole to get that decimal that went into that box. D. D, this is an A or a B situation. Okay, so now I need the A or I need the B situation. Okay, so now I got to actually do a little bit here. So I got to do the probability of A plus the probability of B minus the probability of A and B. Okay, so what was the probability of A? 0.3. What was the probability of B? Well, I never did the probability of B, but the probability of B is right here, 6/10. Minus the probability of A and B. Remember, this was A, this was B, this was A and B. So 3/10 take away 2/10 is 1/10. 1/10 plus 6/10 makes 7/10. I have a total of 7/10 for A and B. Probability, or A or B. A or B, 7/10. Almost done. Letter E. This is an if statement. So in letter E, I have probability of A if B. So I'm going to write that down. Probability A if given B. So again, and of these two. So let's do A and B divided by probability of this one. A and B. A and B, 0.2. B. I'm not sure I have B. It's somewhere. Oh, right here. 6/10. Take your calculator. 2 divided by 6 is 1 divided by 3. That's 0.33 when you round, because it's 0.3 repeat. Letter F. I think it just switches around, right? Yep, B of A. So probability B given A. B given A still means A and B, but this time we divide by A. Move my mouse there. So it's still 0.2 because that's still A and B, but now I need probability A. Remember, probability A was 3/10. 2 divided by 3 is 0.6 repeat. 0.6 repeat is 0.067 when rounded to 2. Letter G. Are events A and B disjoint? No. How do you know that so quickly? Because there's numbers everywhere. In the chart, there's numbers. If there's numbers everywhere, there's no zeros. That's why. If you have to explain it, because there's an event for everything. Everything has an event, so therefore they cannot be disjoint from each other. Now, letter H is going to require a little bit of math. Are A and B independent of each other? Okay, well, if A and B are independent of each other, A has no influence upon B, and A and B mean the same thing. So in order to test, here's what we test. We're going to take the A and B calculation, and we're going to ask ourselves if it is equal to the probability of A times, time sign, probability of B. Okay? If this is true, and that's the event we're checking, A and B. If it wanted some other event, and we only have A and B, so we can't check anything else, we'd have to do other letters. Okay, so let's do, first of all, the AND calculation. Go up here, right there, 0.2, A and B. If this is going to be if this is going to be truly independent, then these two things will match. If this is not independent, then these two things will not match. Now, let's go find the probability of A. We already know that right here at 0.3. Let's multiply that times the probability of B. Where's the probability of B? Probability of B is 0.6, I think. Yep, 0.6. 3 times 6 is 0.18. 0.2 does not equal 0.18. So the answer for this is no. They are not independent. If they were truly independent, these two numbers would be dead on the same, whatever the heck they are. Your summary for this chapter is that all of these rules are a super important aspect to what we're doing. So know how to use the rules. In addition, you can see tonight I also showed you how to use the table very well. That's given the fact that you have a table. So you can't always bank on the fact that I'm going to have a table. You have to be able to calculate these rules. These rules will be available to you. You can draw right from them like I did. If A and B are disjoint, remember their AND situation is 0. Excuse me. If two things are independent, though, independent is different. And I just did the calculation for independency to where the A and the B has to equal the probability of A times the probability of the B. Hope this was helpful to you. I would probably suggest going back over it, looking at the spots that hung you up or the parts that you want a little bit more work on. Other than that, we'll be moving on to the next chapter. Have a great day.